Brilliant calculus students, today we're going to learn about Taylor series. We have a graph of cosine over here, and let's say we wanted to try and approximate some value here. So we have it from about negative pi to pi over here. It's about here and here. But let's say we wanted to approximate the y value of 1/4 or something. Something like that. So what is this y value? And we know that it's going to be close to 1. Because of just the nature of cosine, but let's try and estimate that value. We're going to do so without a calculator. So what you might do is you might say, okay, so it's close to 0, and we know the value of cosine 0. And the value at cosine 0 is 1. So I'm just going to write that over here. I'm going to write that in blue and say that let's call f of x cosine x, f of x equals cosine x, cosine x, and we're going to just call the point that we are evaluating at initially. We're just going to call this value of initial where we're going to measure, we're going to approximate the cosine value, and we're going to call this initial value c. So we're just going to say f of c. I'll write that in green. I'll say f of c, f of c is 1. And so what Taylor series allows us to do is to approximate functions that may not be as easy to calculate. And we can do this by hand and approximate it to a good degree of accurateness. And we could do so without a calculator. Transcendental functions like cosine, sine, e to the x are kind of weird functions, and so we like to approximate them using some of our calculus techniques. And so we know that just looking at this first term, we can approximate this as 1, but there's this little discrepancy here, which I'll highlight in yellow. And it may not seem like a lot, but in terms of sine and cosine, that's a big amount. So let's try and go and look at it again from another perspective. So we have that the first value here is 1, but what if, to get a more accurate answer here, we might want to start looking at the derivatives. And so we know that the derivative of cosine f prime of x is negative sine. So cosine x is equal to, or the derivative of cosine x is negative sine x. And so now we know that, now that we have the derivative, we can try and calculate specifically the derivative at that point, f prime of c, which is 0. We're looking at x equals 0. And so that is 0. Sine of 0 is 0. And so that we know that this horizontal tangent line we know that this tangent line at that point is horizontal. And we continue this idea. We could say that f double prime of x is negative cosine, taking the derivative again, negative cosine, negative cosine x. So what we would do here instead is say that when we take we say f double prime of c, that is, so if we know that cosine at 0 is 1, the negative of that is negative 1. So we know that it is concave down, which we can see from the graph, but if we didn't know that, we can see that it's concave down, as the second derivative is negative. But what if we wanted to try and graph a quadratic equation to where it kind of matches the slope of the function at this point? What if we wanted to try and do something like that? We have a point that matches cosine at that, and we have a linear function, but what about a quadratic? So we're going to start with the term a, and normally you have ax squared plus bx plus c in an algebra class, but to make this a bit easier to add on terms in the future, we're going to write this as a plus bx plus cx squared and plus dx cubed, and then continue down the line. But we're going to stop at just cx for right now. We're going to stop at c. And then we're going to take derivatives. We're going to take consecutive derivatives with respect to x. And so this first derivative is b, and then plus 2cx. Next, the b term goes away, and it's just plus 2c, or it's just 2c, 2c. So now that we've done this, we can start solving for values of a, b, and c so that we can find a equation to graph this. So we know that the initial value is 1, and so when x is 0 in both cases, the b and c terms cancel out, and we're just left with a is equal to 1. So I'm just going to say a is equal to 1. We also know that in the scheme of the second derivative, that f of 0 is negative 1, or f double prime of 0 is negative 1. So we can set this equal to negative 1. 2c is equal to negative 1. And then divide both, because this is the second derivative here, we can set 2c to be negative 1. And then we can solve for c by dividing both sides by 2. And we can now say that the coefficient of c is minus 1/2, dividing both sides by 2. c is equal, the coefficient of x squared is equal to negative 1/2. Looking at the first derivative, we know that this is equal to 0. I'll say that I'll just put equals 1 over here just to complete the set. And then because this is equal to minus 1/2, we know that when x is equal to 0, this cancels out, meaning that b is equal to 0. b is equal to 0. So now we have our equation. We have that 1 plus 0x plus minus 1/2 times x squared is about equal to cosine x, at least at x is equal to 0. Let's plot this and see how this works. Here's the graph of 1 plus 1/2 over x squared, or negative 1/2 over x squared, uh, kind of compared with cosine x. And you could see that up until about x is equal to plus or minus 1/2, this is a very good approximation. Like anything between negative 1/2 and positive 1/2 is basically the same value. Look how accurate that is. So we can estimate anything using kind of in this interval to very good precision. And to demonstrate how good this is, I'm going to say, let's compute the value of 1/4 here. No, this is 1/2. This is 1/2. So let's say x is equal to 1/2. 1/2. Using our, this is a kind of Taylor series approximation for cosine x. This is what this is called. This is what we did here, creating a Taylor series approximation for this function. So at x is equal to 1/2, our y value would be 1 plus 1/2 squared over 2. I'll do minus 1/2 squared because we're squaring this, so 1/2 squared over 2. So 1/2 squared is 1/4, and then divide that by 2 is 1/8. 1/8. And then 1 minus 1/8 is 7/8. So the estimation using our Taylor series up to 3 terms, we have not done this very far, is 7/8. And I will check what it is for 1/2. So cosine of 1/2, 1/2 radians is equal to 0.7, I'm sorry, 0.8776. 8776. So that is the exact value. And we got, which is almost exactly equal to the exact value of, so this is what we got, 0.875. That's the decimal form of 7/8. And this is very close. We got to the second decimal point just from 2 iterations. Like, that is very impressive. For functions like sine and cosine, where it is kind of these derivatives are alternating, where it goes negative sine, negative cosine, sine, cosine, it's that sequence, we have these alternating ones and minus ones with zeros in between. And solving for these values of a, b, and c, we start noticing a pattern. So it goes 1, 0, negative 1/2. That's going to go back to 0. It's going to go 1 over 24 as the coefficient. And then it's going to go 0. And then it's going to go back to negative 720. And this looks like a very strange pattern, but we can see this pattern. So these coefficients are basically the factorials. And so we have these zeros in the middle just because of the periodic nature of sine and cosine. So we kind of have these flat tangents from time to time. So that's why you have these zeros popping in there. But these are factorials of the nth degree. So if we take no derivatives, we have 0 factorial, which is 1. This is 0 factorial. We take 1 derivative, 2 derivatives. We have 1 over 2 factorial. 2 factorial is 2. We skip the 0 because it's the cosine here. And we have now 4 factorial. And because it's periodic, we switch between positive, negative, and then we go to 6 factorial. And this pattern continues. And so we can approximate cosine x with this pattern. We could say cosine x, and we could take this out forever. And it would, as we do this, as we take the infinite sum of these, we would get the exact value for cosine x. But we start at 1, and then we go to 1 over, we will do x over 2 factorial, and then we're going to add x over 24 factorial. I'm sorry, 4 factorial, 4 factorial. But this time we have to have our numbers to the same power as the factorials. And because these are ones here, it doesn't really matter in this case, but it is very important. We have these, you have to have the correct coefficient, or the correct exponent. So x to the 6 over 6 factorial plus x to the 8 over 8 factorial. And this pattern continues. And if we did this forever, we would get cosine x. So what if we wanted to write this as an infinite sum? What we would do is we would write our sigma, and then we're going to say from n equals 0 to infinity. The infinite sum of these terms gives us our exact value for cosine x. So I'm going to move this over. So how would we go about writing this infinite sum to be exactly cosine x? So we have these alternating plus and minuses. So we're going to have a negative 1 out front, and we're going to say to the n. So that way we just have a alternating plus minus plus minus. And this will never be greater than 1 or less than negative 1. So it's going to be either negative 1 or 1. So it's just going to alternate back and forth. Next, we need to have the power be growing by 2. So we have technically x to the 0 here over 0 factorial. And then it goes to x squared. So we need to have an x to the 2 times n, because this is a even power, and we are incrementing by 2 each time, and we want the power to be even. If we said plus 1, that would be in the form of an odd number, but we only want even powers. So we're going to have x to the 2n, and then we also want that same power to be factorial. So we're going to have this 2n factorial. We're going to have the same exponent as whatever number factorial. And so this is how you would write an infinite sum for cosine x. And this is all done with some algebraic. This is just polynomials. So we could do these in an algebra class. If someone's wrote out the 5th degree and just said, hey, estimate the value using this, you could do this in an algebra class. It's just this taking derivatives part is where you use the calculus. So I hope that helped with Taylor series. Bye.